Alright students, it's time for lecture 2. Thought we should have some theme music here for this one. Jazz this one up a little bit, break it down. So today we're going to finish talking about slip, and we're going to talk about strengthening mechanisms. Alright, so let's get into it here. And if anyone can name that music without doing some kind of capture software, I'll give you extra credit. Alright, so let's see. Let's finish talking about slip. So we did some examples with slip systems, resolved shear stress, critical resolved shear stress last time. Let's just talk a little bit about other deformation modes. So when we talk about deformation modes, that is, how do metals deform? And by far, the most important deformation mode is slip. So, talk about slip, which we've already talked a lot about. So that's planes of atoms slipping past each other. The other deformation mode of importance is twinning. And we talked about twinning back in chapter 4 a little bit. We talked about that being a mirror image defect that can form across a plane. In this case, the deformation mode is where the lattice sort of rotates, atoms sort of rotate around a plane. And that really becomes important in a couple different circumstances. So, you know, slip is planes of atoms or blocks of material slipping past each other. Twinning is more like a rotation of the lattice. And I'm going to show you some pictures, I think, that do a better job than I can describing this. But it is important in BCC and HCP materials, especially at low temperatures, low temps, and high strain rates. What do we mean by that? Well, like shock or impact loading. So very high strain rate loading. You know, we've been talking about slip. We've been talking about, you know, more static type loading. So this is more dynamic loading. And I'm going to go to a couple figures here that describe that. So this was a figure that we talked about before. And here you can see sort of atoms shifting around a twin plane there. And I want to show you the next as a result of a shear stress. So the atoms kind of rotate from their positions, they kind of shift. I think the next figure kind of shows what's going on a little better in comparison to slip. And that is, you can see for slip planes, blocks of materials in sort of discrete blocks slip past each other. For twinning, a block of material in the crystal kind of rotates around these slip planes. And you can kind of see a couple differences there. But this is an important deformation mechanism, but not as common or important as slip. But I did want to mention it because it is common in those materials and cases we just mentioned. So I want to talk a little bit before we go into strengthening mechanisms about, because it leads into it, slip in polycrystals. So we spent a lot of time, in fact the whole last lecture was slip in a single crystal. Now we're going to talk about slip in polycrystals, and most materials are polycrystals. So let's note a few things here. First of all, we're going to say polycrystals are generally stronger at room temperature than single crystal materials. And what we're going to say, the reason why, and I'm going to draw a little figure that goes along with this, but we're going to say even though one grain or crystal in the material may be favorably oriented for slip, we can say it can't slip until adjacent grains that are maybe less favorably oriented can slip. So let me draw a picture of what I mean here. And this is going to lead into our discussion of strengthening mechanisms. But let's say we've got a polycrystal of material, and it's got, we've got some grains in here like this. And each one of those grains has a certain orientation of the slip planes relative to the stress. Let's just take, we'll call this grain number 1. Well, right now grain number 1 looks like it's more favorably oriented for slip. Grain number 2 is less favorably oriented, but grain number 1 cannot slip, it can't deform until the one next to it can deform also. So on average, what we can say is that the stress required to make this thing deform increases from, just having a single crystal on average. And that's kind of shown in this figure I've got here to the right. So this is related to a figure in your book. Here, let's look at this figure. So this actually shows a single crystal of material, or sorry, a polycrystal material that has been deformed in compression. And what you can see there is you can see outlines of different grains. Here's a grain right here I'll outline. Here's another grain over here we'll outline. But you can actually see in there evidence of how the slip planes are oriented different in different grains, and you can also see that several slip systems operate on these different grains. So you can see actually some slip lines this direction here as well as this direction. So remember, we've got multiple possibilities for slip. There's more than one set of planes and directions normally. And I like this figure because it kind of goes back to what we just said with, the idea of polycrystals deforming, but it also goes back to our discussion of slip systems and, slip planes and directions. And it's also going to lead into our discussion of strengthening mechanisms here, which we're going to talk about. So that's a very important thing to take away from Chapter 7, and that is, how do we strengthen metals? I think you could probably name some ways, but we're gonna talk about the three fundamental ways of strengthening materials. They are grain size reduction. So I reduce the grain size. Solid. So here, let's just put, so this is more grain boundaries. We're going to put in parentheses, you know, another term for this. This is, second is solid solution. We talk about solid solutions, strengthening. This is also known as alloying. So I add zinc to copper to make brass, for instance, and it makes the copper stronger. And then the last one, which we've already hinted at some, is strain hardening. And what is that doing in the material? Well, we already talked about this. This is adding more dislocations or increasing the dislocation density. So we're going to talk about each of those in turn today. So let's start with grain size reduction. Actually, let me back up for just a second here. Before I go on, I just want to reiterate that all these things that we do to strengthen materials goes back to making it more difficult for dislocations to move. Everything we do to strengthen a metal goes back to dislocations, and so that's why we spent some more time in Chapter 7 talking about why they're important. Because really all these things we do to strengthen a metal goes back to making it more difficult for these dislocations to move, or more difficult for slip to occur. We could say it another way. Okay, so let's talk about grain size strengthening, and we'll show some figures from your book. So let's look at the first one, grain size strengthening. So if we decrease the grain size, so grain size goes down, strength goes up. Now, so let's take a look at a grain boundary in a crystal. I'm going to draw a schematic, and I've got a better figure from your book. But let's draw a dislocation here in a material. And we'll put some atoms in here. So here's a dislocation right here. And so here's our lattice. And let's say there is a grain boundary right here. So I'll put a line there. And over on this side, we've got a crystal as well. But it has a different orientation. So we'll draw it like this. Well, in order for this dislocation here, I'm going to change colors for a second. Remember, it's a shear stress that causes this dislocation to move. So if this dislocation here moves over to the right here, it kind of gets stuck at the grain boundary. So if I want to continue that dislocation moving in another grain here on this dotted plane here, it is sort of constrained to do so. Maybe we'll put it like this: the grain boundaries act as a barrier to dislocations moving. In other words, this dislocation moves along and it gets stuck at the grain boundaries. And so if I can create more grain boundaries, so we can say finer grains, smaller grains mean more barriers or more grain boundary area. So the finer the grains, the smaller the distance a dislocation can move before it kind of gets stuck against a grain boundary. And then it can't move. Or I really have to increase the stress a whole lot to make it keep moving. Now, there is a famous relationship in metals called the Hall-Petch relationship. We'll take a look at here. That has to do with grain size strengthening. So it's called the Hall-Petch relationship. And I'm going to write it down, but basically what it looks like is this. The yield strength equals sigma 0, which is a constant, times k sub y, which is a constant, times d to the minus 1/2. So let's define some terms here. So this is the strength, yield strength. These are just constants for the material. So these are material constants. And d is the grain diameter. So you can see, I could write this another way. Let me go back here. We could write it like this. Sigma yield strength is sigma 0 plus k over the square root of d. I'm just rewriting that in a different way. But you can see as the grain diameter goes down, the yield strength is going to go up. So let's take a look at a couple figures from your book. Here's this figure that we talked about. You know, a dislocation moving on a slip plane, and it gets stuck at a grain boundary. And if we go back to this equation for the Hall-Petch relationship, if we plot the yield strength versus 1 over the square root of the grain diameter, we get a linear relationship. So here's the yield strength versus 1 over the square root of d, that as the grain size goes down, so here's this figure here, as the grain size goes down, so here's 1 over the square root of d. The yield strength goes up. So you can see this factor 1 over the square root of d. So that's kind of shown here in this plot. So this just shows the yield strength as you decrease the grain size. So they're showing you the grain size in millimeters, or we could write it in micrometers. It doesn't really matter. But this is a very famous relationship because this is one of the fundamental ways to strengthen a material. Now you may say, okay, so how to make smaller grains? We've talked about this before, but I'm just going to review it very quickly. And the answer is so-called thermomechanical processing, or heating, in other words, heating plus working the metal. And we're going to talk about working and heating in this chapter. So it takes special processing to decrease the grain size, but that's something that we do in metals. Okay, that's one of the reasons we work and heat metals, is to reduce the grain size. In fact, there's a whole special class of steels for structural steels. They're called high-strength, low-alloy steels. And the way they're strengthened is not by adding alloying elements, it's by decreasing the grain size. Okay, now let's talk about solid solution strengthening, or alloying. Sorry about that. Let me erase that. Solid solution, right? It's like a solution, but it's a solid. We've already talked about solid solutions. That's like an alloy. Solid solution strengthening, or also called alloying. Right, I'm adding alloying elements. I add carbon to iron to make steel, or I add tin to copper to make bronze. Lots of different alloys out there. Let's kind of draw a picture here. So let's make a few comments here. First comment we're going to make is high purity metals are normally very soft and ductile. I mean, think about pure copper or pure aluminum. There's a whole age named the Bronze Age because one of the first metals that we worked with was copper, but it was so soft we couldn't really make any useful tools or weapons out of it. But once people learned that we could alloy it with tin to make bronze, now we could start making something that was much, much stronger. Now, alloying, we'll say this, alloying elements can be substitutional. Right, we talked about substitutional solid solutions, or interstitial. Oh, what's an example of substitutional? That would be like tin in copper, because tin's about the same size as copper. Interstitial, that would be like carbon in iron, because we know bunch, like those are the small elements. Either way, what goes on in the material is that you introduce strain into the lattice. So let's draw a little bit of a figure here. So remember, we had a dislocation, and we said that dislocation had a strain field associated with it. Right? We said it was compressive here and tension here. Well, what if over here I've got this really big atom stuck in here where it shouldn't be? Here's our small atoms, or smaller atoms. Do you all see that this thing is kind of too big, and so the lattice around here is also strained? So when a dislocation comes up upon this element in solution, these strain fields start to overlap, and it doesn't really like that. It takes more stress to make that dislocation move through there. So I've got this, strain in the lattice. We also know that dislocations have strain. So the more alloying elements I get in there, the more strain in the lattice, and the more it interacts with dislocations. Now also, interstitial elements, well, actually let's say it like this. Elements may preferentially occupy space near dislocations. Well, what do I mean by that? Well, let's take a small element here. So let's say I've got iron. The small elements of carbon like to fit in, in these little spots in here. Because it fits in there a little better. The lattice is kind of stretched, so those elements can fit in there a little bit better. The same thing goes for bigger elements. They can fit in there also a little bit better. So, maybe I've got a big element in there. So maybe this is something like tungsten in iron. Well, that's more stable. So what we can say is it's more difficult or harder to make dislocations move away from this. It likes this a little better. So those interstitial and substitutional elements, the atoms tend to diffuse to dislocations and stay there. And now to get the dislocations moving, it takes an extra amount of stress to do that. Now there's some figures from your book here that describe that. Here's this idea. Look, here's an atom that's a little smaller. So there's sort of a tensile field associated with that. So it likes to sit above a dislocation where there's, a compressive field, kind of cancels out. And here is a bigger atom. It likes to sit below the dislocation because we already know there's a tensile field there. We've got a compressive field associated with that big atom, so it kind of likes the spot below. But the point is, it likes this, so it takes more stress to get the dislocations to move. Now this only kind of works up to a certain point. I've got a figure, so let's talk about adding copper to nickel. So, we'll just say alloying only strengthens up into a certain point. You just can't keep adding things forever. So if you plot the strength of copper alloy as you add more and more weight percent of nickel, so let's look as an example a copper nickel alloy. So as I add more and more, so here's the hardness of pure, or strength of pure copper, and as I add more, it peaks around 60% nickel, and then it kind of goes back down. And there's a figure in your book that talks about this, so you can see here the strength with nickel content, but you can also see that something happens to the ductility. So as we add more and more alloying elements, go back to this figure here. So as we add, the strength goes up, but we could also plot the ductility. This is an important relationship that we're going to see again and again. The ductility goes down and hits a minimum at 60%. So there's an inverse relationship between strength and ductility. The stronger we make things, the less ductile they are. And that's shown in these figures from your book. It shows that the ductility, which is down here, goes down. It gets a minimum. It's a minimum where the strength is a maximum. All right. Next concept here. So we're on number 3. So item 3, and that is strain hardening or cold work. So strain hardening, or sometimes called cold working. Well, we've already talked about this. In fact, we talked about it in chapter 6 when we said if you look at tensile behavior and you go past the yield point up to here, if you unload and reload, the strength has now gone up. You remember that? Here was the strength to begin with. Here's the strength here. So remember, as we deform it, the strength went up. Strength goes up. So that's this whole idea of strain hardening. As we strain the material, the strength goes up. Now what's going on in the material? Well, we said that this is associated with plastic deformation, or straining the material, creates more dislocations. So as we work the material more and more, the dislocation density gets higher and higher. And that's the idea. And we said before that the dislocations tend to interfere with each other. So we'll draw some pictures of that. All right. So let's keep going on with this concept. This is an important concept, and we'll talk a little bit about how we do this in metals. How do we actually strain them or cold work the metals? So, well, we do that through processing. Lots of ways to do that. So that's rolling, forging, any kind of deformation, extrusion, drawing, any kind of forming operation where we're deforming the metal. So rolling, forging, drawing, extrusion. And I have some figures here to go along with this. But remember, this goes back to our discussion that we had a few days ago. That is, if you get more and more dislocations, they start to interfere with each other. So this dislocation over here doesn't go very far before it runs into another one. And remember, we said they exert forces on each other. So the dislocations interact with each other. Let's put that up here as a reminder. The dislocations interfere with each other. And how do we increase the dislocation density? Through processing. So all of those things, so there's a figure from your book. That describes ways that that's kind of schematics here of how we deform metals. So up here we've got forging. That's where we take a die of a certain shape and we smash it into that shape. An example product like that might be like a wrench. And if you look at that wrench, sometimes it says drop forged on it. Well, what does it mean? Well, it means I take a die in the shape of the wrench and I smash the metal into that shape. We've got rolling here, obviously, on the right. Well, we don't roll things just to get them in the shapes that we want. We roll it because it deforms the metal. It can make it stronger. Down here we've got extrusion. I think we've already talked about that, but that's like the Play-Doh fun factory of metals, where you've got a die of a certain shape, an opening of a certain shape, and you push with a lot of pressure and force the metal through the die, just like Play-Doh. And then over here we've got drawing, which is very similar to extrusion, except instead of pushing it through a die, we're pulling it through a die. Some common materials that are extruded and drawn. So an extrusion might be like a window frame, an aluminum window frame, where it's like a kind of a weird shape, maybe a box shape or something like that. So you just push it through in that shape. Drawing might be a wire or a rod shape. So drawing is a common way to make wire and small rods and things like that. So those are the ways that we work materials. Now let's talk about how do we quantify the amount of work that we're putting into a material. So how to quantify the amount of strain hardening or cold work. Well, we can look at these different processes, but the easiest one to look at is maybe rolling. So here we have a material going through some rolls, comes out on the other end and it's much thinner. So the rolls are rolling like this. Comes out on the other side much thinner. So we can often quantify this by the amount, literally the amount that you squish this thing. So we could do it by the, we can sort of quantify by the percent reduction in area or thickness. So as this thing goes through here, the area is getting much smaller. So here's the final area, here's the initial area. Or you can measure the thickness. Here's the initial thickness and the final thickness. So we could write some equations, but we could quantify the amount that we're working the material by literally how much are we squishing it. So you just plug in, how much did the area decrease percentage-wise? That's related to how much did we squish this thing out. Or we could do it by the reduction in thickness. The more we squish it out, the more work we're putting in the metal, which kind of makes sense if you look at those equations. And if we plot what happens to the strength as we work the metal more and more, we get a relationship that looks like this. So here's the strength versus how much, that's percent cold work, or how much we're working the metal. The strength goes up like this, kind of levels off at a certain point. So here's our strength. And what happens to the ductility? Well, here we'll plot the ductility over here. The ductility goes down. The more we work it, the stronger it gets, but less ductile. Well, let's take a look at some figures from your book here that describe this relationship. So first of all, here's tensile behavior as we work the metal more and more. This is a steel, so here I'll draw it over here. So let's look at tensile behavior as a function of cold work. So let's look at stress strain curves. So this has very little cold work, so it's really ductile. More cold work, so maybe this is 0% cold work, or that's in the soft condition. Here's 10% cold work, 20% cold work. One thing to notice there is the ductility goes down as the strength goes up. And also you can see that I drew all these to have the same stiffness, because processing doesn't really affect the stiffness of the material. The only way that you can affect the stiffness or that slope is by changing the fundamental composition of what it's made out of. Now, this is a figure here from your book of different steels, cold work to different amounts, and you can see the more I work it, the stronger it gets, but less ductile, which makes sense. We've talked about that quite a bit already in this class. There's always a trade-off. That is one of the big trade-offs in materials and metals, is usually the stronger it is, the less ductile. We want both. Remember in chapter 6, we want both, because if we have high strength and high ductility, that means high toughness, right? The area under the curve. Now going on here, here's a figure from your book that describes what happens to the strength of steel, brass, and copper as we work it more and more. And you can see what happens to the ductility. So the left is the strength here, so here's the strength. As we work it, the strength goes up. You can see steel's already much stronger than those other alloys, but you can see there why brass is used as an alternative to copper, because it's much stronger. We add some alloying elements, you get a big increase in strength. And then the more you work it, the ductility goes down. Now let's talk about one last thing, and that is changes in the microstructure due to cold working. Changes in microstructure for cold working, or strain hardening. Remember, it's the same term. So changes in microstructure, well, first of all, let's say we've got a metal that's got a certain grain size here, and we put it through some rolls. Well, the grains tend to get squished out and elongated in the rolling direction, or forging direction, or whatever process that we're using to work the metal. We get sort of a preferred orientation here. So now, before the grains were so-called, uniform and random, this material on the left is somewhat isotropic in that the properties are pretty uniform. Afterwards, it's squished out. It's not randomly oriented anymore. Now it's not isotropic anymore, or anisotropic. That has some important implications for materials and metals. If you've got a rolled out plate of something, here's a figure from your book. Over here we've got a fairly uniform microstructure on the left. On the right we've got a rolled microstructure, and you can actually see that the rolling direction is this way now. But the grains have been squished out there. But depending on how, let's say you have a plate of material that's been rolled like this, and you machine out a part in this direction, it's going to have much different properties than in these directions, okay? So it's not isotropic anymore. And that's one thing that is critical, especially for some of you mechanical engineers, to take away from this class, is real materials are not isotropic often, and you've got to be careful about that, because a lot of times in your calculations and designs you might assume that, but it's not true, especially when we start processing metals. All right, so we're going to end there, and next time what we're going to talk about is something that we've already hinted at, but we said before that the more you work the metals, the stronger they get, but less ductile. How do we return them to be soft and ductile again? We heat the materials. That's called annealing. So you have a reading assignment that's going to be due the Friday after spring break on that. I'm going to email that out to you. And that is basically a reading assignment to read about, well, what happens when we heat up a material? Why does it go back to being soft and ductile again? So that's what we'll talk about next time. So next time we're going to talk about heating, or going back to being soft and ductile again. It's kind of like reversing what we did when we were working the metal. How do we go back the other way? So that's what we're going to talk about next time. So don't forget, you've got a reading assignment 11, which I'm sending out by email. It's due Friday, March 11th. The Friday after spring break. Wait, is it the 11th? Let me check here. It is, no, that's Monday. The 15th, sorry. It's assignment 11 due on the 15th. Okay. But you need to read that, because it's really a concept thing. There's not a lot of calculations necessarily. It's concepts. It's what temperatures do we heat things to? What happens inside the material that erases all of the cold work that we did to go back and be in soft and ductile again? All right, students, so make sure you read that. That's very important reading. That's the end of this lecture.